this section we're going to talk about how priorities work with time loops, and we'll talk about how you can configure time loops as well. So what you see on this slide is a time loop on a block diagram. Notice there are 4 different parts to it. There's the input node, there's the left data node, and also the loop in which code executes. There's also a right data node, and there's an output node. To configure the time loop, you can double-click the input node, and that'll launch a configuration window where you can set different parameters. You can also set these by wiring values into the input node as well. The left data node is going to communicate information about the previous iteration of the time loop. The right data node is going to allow you to wire values to it to configure the next iteration of the time loop. And the output node will return information from the final iteration of the time loop. For example, whether the final iteration completed on time or any errors that occurred during the loop execution. One of the main parameters that you'll configure for a time loop is its priority. Okay, so now let's talk about what priority time loops in general execute at. So if we take a look at that bottom screenshot there, in the previous section we talked about different VI priority levels. So remember we talked about there's normal priority, above normal, high, and time critical priority. So all time loops will actually execute between high priority and time critical priority. So if you have a time loop running, no matter what, it'll preempt any VI that's running at normal priority, above normal, or high priority. But if you have a VI set to time critical priority, that time critical priority VI will preempt time loops. So generally, when you're using time loops for priority, you're going to have all your VIs set to normal priority. That way you know that your time loop will preempt any of those normal priority VIs. And we'll talk about this more in detail later. But for now, just remember that all time loops will execute between high priority and time critical priority. Here we see the configuration window for your time loop. So if you were to double click that input node on your time loop, then it would open up this window and allow you to configure it using a window. So there are several things you can configure here. For example, your loop timing source, you'll see that there's a place to define the period of the time loop and also its priority. And we'll talk about several of these settings in the next couple slides. Okay, so let's talk about the priority setting first. So for each time loop, you can set its priority to a number. So the higher the priority value, the higher its priority relative to other time loops. So for example, if I had a time loop set to 100 and another time loop set to 50, the time loop that's set to 100 will preempt the time loop set to priority 50. So the higher the priority number, the higher priority this time loop will execute relative to other time loops. Priority values can range between 1 and 65,535. But remember, no matter what priority you set in this configuration window, all time loops will execute below time critical priority, but above high priority in relation to ordinary VIs. Okay, so next let's talk about the timing source. So the timing source is going to allow you to choose what clock or timing source is timing your time loop. So by default, if you drop down a time loop, the default timing source will be the 1 kilohertz clock of the operating system. So because it's using the 1 kilohertz clock, that means your maximum execution is going to be once every millisecond. a 1 kilohertz clock is going to have a millisecond resolution. There are other timing sources that you can use as well. On many real-time targets, there's going to be a 1 megahertz clock available. So if you choose the 1 megahertz clock, then you're going to get microsecond resolution. You can also sync your time loop to the scan engine. If you do that, then the time loop will execute after every scan is finished. So that way, it'll be synchronized with the scan engine. You can also do other timing sources, such as sources coming from a DAC device. So for example, you could have your time loop execute an iteration every time a digital line changes. Also, you can use a hardware clock from a DAC device, or you can even wire in an external clock to your DAC device to time a time loop. Here we see that we can also define what the period of the time loop is. So instead of using a wait function inside a time loop, you would just define the period within these parameters itself. So notice that you can set the period here to 100 milliseconds. That means this time loop is going to execute an iteration once every 100 milliseconds. Also, there is a setting for offset. So if you want, you could have the time loop execute with an offset as well. So for example, let's say we had 2 time loops, and they're both executing with a period of 100 milliseconds. If you wanted them to both execute with that same period, but you wanted one offset by 10 milliseconds, that's how you would accomplish that. You would set both time loops with a period of 100 milliseconds, and on one of them, you would make the offset 0 milliseconds, and on the other one, you would make the offset 10 milliseconds. The timing source is going to determine the time unit of the period and offset. So in this particular screenshot, we see that the units are milliseconds, which means it's probably using a 1 kilohertz clock. If you're using a 1 megahertz clock for the timing source, then instead of milliseconds here, you would see microseconds. Another thing that you can set in the configuration window is the name of the time loop. So if you look at structure name, you can set it to something a little bit more readable. By default, it'll be a random alphanumeric string. In this case, we've named it to example. We could also change it to something like control loop. So notice whatever you define in this window on the right-hand side, you can have it show up on your actual time loop itself to kind of document it. You can also use this name programmatically. So for example, there is a VI called synchronized time structure starts, and by using that VI, you can input 2 time structure names to have them start at the same time. So for example, if I had a time loop called time loop 1 and another time loop called time loop 2, I can refer to them programmatically using the synchronized time structure starts VI and have both of those time loops start at the same time. So let's talk about some monitoring and debugging functionality that's built in to the time loop structure. So if we take a look at this screenshot on the bottom, we see that there's a time loop, and I want to point you to the left data node over there, and it has an item called finish late. So let's talk about this. The finish late item here will output a true if the previous iteration of the time loop finished late. So for example, what's the period of this time loop? If we look on the input node, notice that the DT item, which is the period item, is 1000 milliseconds. Okay, so this time loop is set to run once every second. So if on the previous iteration of this time loop, it took 2 seconds to run, then we can get that information and notice that finished late over there, it would output true because the previous iteration took longer than the specified period. Okay? This way we can monitor if the time loop is running on time. So what are some ways we can use this finished late output? One thing you can do is you can display a running count of how many iterations did not complete before the expected deadline, which is what we see here in this block diagram. Notice that every time finished late equals true, we increment a finished late count inside that case structure. Okay? And that way, when we're looking at the front panel, we'll know how many times it's been finishing late. And if it's been finishing late many, many times, then there's probably something we need to adjust in our code. Also, time loops, because they run at a higher priority, a lot of times what we use them for is for deterministic code. So deterministic code, by definition, is code that we want to typically run on time every time. So one other thing we can do is if it finished late equals true, then we know it didn't run on time for that previous iteration. So one thing we can do is if finished late equals true, we can send the application into recovery or a safe shutdown mode or some code to just handle the fact that deterministic code finished late. another item that we can use on the left data node is the iteration duration terminal. So the iteration duration terminal will output how long it took for the code inside the time loop to execute. Okay, so this is not the same thing as the period. This is saying how long the code inside the time loop, so for example in this case, the functions that you see inside the time loop, however long that code took to execute, that's what the iteration duration will output. So notice over here, the period, the dt over there, is defined at 1000 milliseconds. If the code inside the time loop took 10 milliseconds to execute, then iteration duration would output 10. So what could you possibly use this for? You could use it to monitor a running average of the loop iteration durations. So notice in this case, that's what this code is doing. It's taking a point-by-point input, and it's taking the average of those points. And it's telling us what's the average iteration duration of the last 100 points. Also, if the loop happens to finish late, you can use the iteration duration terminal to calculate exactly how late. So if the code, for example, took 2000 milliseconds to execute in the previous iteration, we can actually get that information. So if we saw that the finish late equals true, we can use the iteration duration to say, okay, well, how long exactly did that code take to execute that previous iteration? So we can figure out how late the previous iteration was. Okay, so let's open up LabVIEW and take a look at the time loop configuration there. Okay, so let's take a look at time loops in LabVIEW. So what I have here is I've got my project, I've got my RT target, and I am using a BI that's running on my RT target. And I'm going to go to the block diagram now. Okay, so the way that you would get a time loop on here is you would right click, go to structures, time structures, and here we have a time loop. So I'm going to select that, and then you would just place it down just like you do with a while loop. Okay, except it looks a little bit different. Okay, so notice here we've got our input node, we've got our left data node, right data node, and output node. Okay, so one way that you can configure your time loop is you can double click this input node. So here I've double clicked it. Notice in this window, here's where I've got my different loop timing sources. Okay, so I have a 1 kilohertz clock if I want milliseconds, and if I want microseconds, I can choose the 1 megahertz clock since that's supported on this RT target. You can also synchronize it to the scan engine if you want it to execute every time the scan finishes. For now, I'm just going to leave it on the kilohertz clock for millisecond timing. So notice here it says milliseconds, and here it's microseconds. So let's go back to milliseconds. Okay. Here, this is where you would define the period. So in this case, I want this to execute every 1 second. Okay. If I wanted to do 2 seconds, I could do 2000 milliseconds. Okay. Let's set it to every 1 second. Okay. So the loop period will be 1000 milliseconds. Here we have period. So for example, if we had multiple time loops, if I had one executing with priority set to 100 and another one set to priority of 500, then if they ever have to fight for resources, the one with 500 is going to preempt the time loop with a lower number of 100. Okay. The other thing I want to notice is the structure name. So the structure name here is just some random number. In this case, we can give it something more descriptive. Maybe this is my control loop. So I can type in control here, and I can have this show up on the block diagram just to help document things. Okay, so that's all we'll talk about for now, and I'm going to click OK. So notice those settings that I set are, you can see them right over here. Okay, so notice that the period here is 1000 milliseconds, and then here the priority is 500. And if you want to show something else, you can just left click on any of these, and let's say I want to show the structure name instead. Okay, so if I select that, notice that my structure name is control. Okay, so this is one way I can say, oh, well, this is my control loop. Okay. One other thing I wanted to note is here, this shows what the what you configured inside that configuration window, but you can overwrite that also with simply coming in on a wire. Okay, so if I was to right click this and create, let's say, a constant or even a control, notice that it's going to overwrite whatever I configured. Okay, so here maybe I change it to every 2 seconds. Okay, so now the period of this loop will be 2000 milliseconds. Okay. So let's just take a look at that quickly for now. So I'm going to create an indicator. Let's call this iteration, and I'm going to create a stop button. Okay. So if I was to run this, I should see this iteration terminal update every time there's an iteration of this time loop. So how often should I see this iteration terminal increment? Well, if we take a look at this, we would say that the timing source is 1 kilohertz, so the timing is milliseconds, and our period here is 2000 milliseconds. So my iteration terminal here should update once every 2 seconds. Okay, so let's go to our front panel, and iteration is right over here. If I was to run this, save it. Notice that the iteration every 2 seconds, it's going to update. Okay. So let me stop that. Okay, let's go back to our block diagram. So here, let's talk about the left data node. Okay, so remember we talked about in the slides, you can actually get some information about the previous iteration. Okay, so all of these are going to be things that you can do to get information on, and you can get information about the previous iteration's timing. Okay, so for example, if I wanted to know if the previous iteration finished late, I would choose finish late, and notice that here I get a true or false to get that information. You can also resize this node, just like you can. So all of these nodes you can actually resize to show more than one element if needed. And here I can choose this, and I can also take a look at, okay, what was the iteration duration? So the code inside here, how long did that take to execute the previous iteration? Okay, so those are two common ones that people would use. The right data node, like I said earlier, is a way that you can modify the parameters for the next iteration. Okay, so for example, if I wanted to change the period for some reason, so if I choose period here, notice that I can now wire a value into it and change the period for the next iteration. Okay, so for example, if it keeps finishing late maybe, and it's acceptable for my application, if it finishes late too many times to increase the period, then I can programmatically increase the period of my next iteration. Okay. Let's see what else. So here we also have an output node. So in the output node, notice that you can get information about the previous iteration as well. So in this case, the output node, if I chose iteration duration here, this would actually be the iteration duration of the very last iteration of my time loop. Okay. So I'm going to change it back to error. And one thing I wanted to talk about to end this with is, let me show you something. So I'm going to show the error input. Okay. So now what I'm going to talk about is the behavior of the error inputs of a time loop, because it may not be intuitive to you the first time you use it. So let's say I had some functions that are before the time loop, and there's a bunch of error wires coming in. Okay. If I was to wire an error wire into the error in of my time loop for this particular terminal, how many times do you think this time loop would execute? Well, the answer is it would not execute at all. So if you wire something into an error in, it treats this whole entire time loop as a node. And because an error is wired in here, and let's say there's actually an error coming in, which means the status element equals true along this error wire, then that means this time loop is going to say, okay, an error has already occurred, let's not even execute and pass that error out over here. Okay? In the same way, so if I was executing some code, and then the code inside here happened to output an error where error wire has a status equal to true, then this is going to exit the time loop right away. Okay. So if that's your desired behavior, then by all means wire it that way. However, if you don't want the time loop to automatically exit if the error status goes to true, then you could just wire it in like this. You could just wire your errors in as a tunnel, like normal, and then handle the wires yourself programmatically with time loop without using these error terminals. Okay. So that's it for this demo, and hopefully that helps bring things together a little bit more. Okay, so now let's talk about the execution inside a time loop. So each time loop only has one thread available. Okay, so let me give you an example of how parallel code would execute within normal LabVIEW. So if you're not in a time loop, and let's say you had a while loop and you had a function and also a wait function, and they were just executing in parallel inside the while loop. Well, when you're running in the while loop, those functions would be happening at the same time, okay, in parallel. However, if you were to do the same thing inside a time loop, so let's say you had, a function and also a wait function that are just on the block diagram in parallel inside the time loop, then only one of them will be able to execute at a time. And the reason for that is, in the previous section, we configured time loops and described time loop priorities. By the end of this module, you will be able to use priorities to separate deterministic and non-deterministic tasks. In some of the previous modules, we talked about some of the advantages of being able to separate your deterministic tasks from your non-deterministic tasks. So in this slide, we see how we can use our understanding of VI priorities and time loop priorities to do this programmatically. The way that we would do this is, if we look at this block diagram, we would put all our VIs at normal priority. And then what we would do is all our deterministic code we would put into a time loop. So notice your deterministic code here is in a time loop, and since there's only one time loop, we know that everything in this time loop is going to execute at a higher priority than the rest of your code. Okay, so you can imagine that you might put your control loop in here or your acquisition code in here because you want that to happen very deterministically and be able to preempt anything else that's going on. And then the rest of your code, the non-deterministic tasks, you would put into while loops. And because everything's running at a VI priority of normal, we know that this is going to execute at a priority lower than our deterministic task. So examples is we could have one of those while loops maybe is handling data logging to file, and another one might be handling network communication, things that don't have to happen on time every time. So in this slide, we just want to further caution you that if you're using this way to prioritize, so if your application is using time loops for priority, then make sure that you keep all VIs at normal priority. We definitely recommend you do this to prevent any undesired behavior. So remember, time loops are going to run between high and time critical VI priority. If you have all your VIs at normal priority, then we know that your time loop is going to execute at a priority above everything else. Then after that, you can use while loops to run normal priority tasks, things that don't need to happen deterministically. Now you can use priorities to separate deterministic and non-deterministic tasks. Next, we will describe the importance of yielding execution in deterministic loops. In the previous section, we used priorities to separate deterministic and non-deterministic tasks. By the end of this module, you will be able to describe the importance of yielding execution in deterministic loops. When you're using deterministic loops, it's important to yield execution properly. So let's take a look at some examples, okay? So let's look at our top example real quick. In this case, we do not have any sleep inside our deterministic loop. So notice at the top, in this application, we have three loops. We have a deterministic loop, we have a normal loop, and another normal loop, okay? So in our deterministic loop, it's just executing code the entire time. Okay, and it's never waiting or sleeping. So it's just continuously executing code inside our deterministic loop. Well, because the deterministic loop has a higher priority, it's going to just keep executing, and it's never going to have time for lower priority loops to execute. So if you notice, the deterministic loop is all blue, continuously executing, and the two normal loops are always waiting because there's never any time for them to execute. Let's take a look at the bottom loop. In the bottom example, we see that there's an adequate amount of sleep time that's added to the deterministic loop. So notice that the deterministic loop, in this sense, it keeps executing, and then that white space with the stripes, notice that it's sleeping that entire time. So it's waiting and adding some sleep to allow lower priority processes to execute. So while the deterministic loop is running, so when it's blue, you'll notice that all the lower normal loops are just waiting. But once the deterministic loop is sleeping, then we see that the normal priority loops, which are executing at lower priority, have time to execute. Okay. In this case, because the other two loops are both normal priority, we just have some round-robin execution between them until they finish. And notice that the normal priority loops have enough time to execute, so they finish, and then we're ready to go for the next iteration, and the deterministic loop is going to start executing again. So at the top, again, we see that no sleep causes starvation, but at the bottom, we see that even if we were to add sleep to the deterministic loop, you might not add enough sleep, and it could still starve some loops. So in this example, you notice that we did add some sleep, but we did not add enough time to sleep. So if we take a look at the bottom normal tasks, notice that we didn't have enough time in that sleep for both normal tasks to execute. Okay, so just keep in mind that when you're using deterministic loop, you have to think about yielding execution and being able to sleep long enough for the rest of your tasks to be able to finish executing. So now would be a good time to do exercise 4.1. I'm going to go ahead and walk through it now. And in this exercise, we're going to be able to adjust the length of code execution and also how much time our deterministic loops are waiting. And we'll see what the effect of that is on our RTVI. Okay, so let's take a look at exercise 4.1, and we'll see how yielding execution in our deterministic loops works here. So I'm going to open up priority trouble, and let's take a look at the code real quick. Okay, so notice that we have a time loop, right? So the time loop is going to be containing our deterministic code because it's going to execute at a pretty high priority, right? So if we look at our VI properties real quick, because we are using a time loop, remember we want to make sure that our VIs are set to normal priority.